Thank you all very much for being here. My name is Ken Goodman. I'm the director of the University of Miami's Ethics Program in our Institute for Bioethics and have the privilege at IDISC of directing the program in Data Ethics and Society. You're here for Meet a Data Scientist, a regular series in which our colleagues here and yonder present their work and describe the many ways in which it affects not just academic life, but life in the world. In fact, if you care about issues related to sustainable infrastructure and clean energy, then you will be engaged by the topic today. Can data science help us understand how nature works? Our presenter today is Dr. Ruiz Pestana, expert in molecular modeling and simulation. His research is focused on understanding the extraordinary properties of nanostructured materials, how that relates to the great epistemological, if not philosophical, question of nature and how we understand its laws makes this exciting for me, and I think others here as well. Without further ado, Professor Ruiz Pestana, the floor is yours. Thank you very much.
Thank you, Ken. Thank you for the nice introduction, and thanks Janina and everybody that organized this seminar. It's actually very exciting to be here. It's very unique, very eclectic people, very eclectic presenters, so this should be fun. So as Ken said, my title is Can Data Science Help Us Understand How Nature Works? So rephrasing that a little bit, what I'm gonna tell you about is can we use data-driven approaches beyond this black box sort of context? And I'm gonna try to keep everything at a high level, but please feel free to interrupt at any point. If something that I say doesn't make sense or you have any question, just unmute yourself and ask. If you write on the chat, I won't see it, so speak up. All right, so let's jump into it. So the talk is gonna have three parts. In the first part, I'm gonna tell you what I do, what my background is, and what I do here at UM. And I think that's important because it'll tell you a little bit about, it'll give you context about how I think about data-driven approaches and also the problems that they drive me. The second part of the talk is gonna be a little bit of philosophy. So I'm gonna give you, I'm not gonna bore you for too long, but I'm gonna tell you how I think data science, engineering, and actual science fit together, or one way I think they can be helping each other out. And then in the last part of the talk, I'm actually gonna focus on a very specific problem that I'm working on. It's a scientific problem where I don't think that data science can, data-driven approaches. When I say data-driven approaches, I mean machine learning. I'm not gonna use artificial intelligence, so it's gonna be all data-driven approaches. So anyway, I'm gonna give you an example of a problem that is very fundamental, where data-driven approaches will actually maybe the only way that we have to make progress there. So all right, so with that, I'm gonna jump into telling you who am I. So I'm gonna start very early on. My formal background is as a structural engineer. So I studied civil engineering in Santander, which is a beachside town in Spain. And for those of you that are not familiar with what a structural engineering does, the job is basically to calculate the forces that are acting on the different elements of a structure. Okay, and we want to make sure that through the design of the structure, those forces are not larger than what the material can support. And to do that, you learn a lot of math and physics, right? So my formal background is these very large structures, which I still love, but I have never actually practiced as a civil engineer. Why? Because soon after my bachelor's, I moved to Chicago. So that was quite a change. I went from a beachside town in Spain to a place in the Midwest where they have to make up words for horrible weather events, like the polar vortex. So anyway, I love Chicago, for the record. But when I started my doctorate, I started working on something very different than our structures. I started investigating why materials have the properties that they have. So you think things like rubber and steel, they have drastically different properties. Why is that? So to answer that question, you have to start looking things at the molecular and atomistic scale, okay? And that's what I did during my doctorate. And I'm gonna give you now two examples of nanostructured materials, two materials that are very, very interesting. They have remarkable properties, and they actually, made me fall in love with this field. So the first example is graphene. All right, so everybody is familiar with pencils, I hope. So pencil leads are made of graphite. And graphite is made of this stack of layers made of carbon atoms, where the carbon atoms are arranged in this honeycomb lattice. All right, so I don't think anybody would suggest that graphite is strong or it could be used as a structural material. So when you isolate one of these layers, what you get is something that we call graphene. Okay, so this is a nanomaterial. Why? Because it's like a 1 atom thick monolayer of carbon. And it turns out that graphene is the strongest material that we know. There is this cartoon from the magazine Scientific American back in 2011, where they first tested the properties of graphene, and it's very intuitive. You need the weight of an elephant balanced on a pencil. I mean, here the remarkable thing is not the strength of graphene, but that the elephant is actually balanced on a pencil. But you would need the weight of an elephant balanced on a pencil head to pierce graphene. That's how strong it is. It's not slightly stronger than steel, it's orders of magnitude stronger. So this to me was surprising, right? Like, how can you go to this nanostructure, change it, and get a material that is, orders of magnitude stronger? Another cover that I actually really like, this is in 1997, way before I started doing research. And this is also to illustrate that the hype is not only on AI. There is plenty of hype in science all the time. So anyway, in 1997, they tested the mechanical properties of carbon nanotubes. So carbon nanotubes are another allotrope of carbon. That means that it's carbon on a different shape. So you can think about carbon nanotubes as basically graphene rolled up. Okay, so the carbon nanotubes were so strong that people suggested that we could build a space elevator. That's how strong they were. Well, it's 2021, that didn't happen. All right. And one last fun fact about graphene, the Nobel Prize in Physics in 2010 actually went to these two gentlemen at the University of Manchester for making breakthrough experiments on characterization and isolation of graphene. So one of these experiments, actually the most important experiments that they developed, it's called the Scotch tape experiment, and it's to isolate graphene, right? At the beginning, it was very challenging to get from graphite to graphene. And this experiment consists in literally using Scotch tape to get some graphene stuck to the adhesive. So the bottom line of this is never give up on the Nobel Prize. You never know. So graphene is one example. When I learned about graphene, I fell in love. It's like, I need to understand what's going on. The other example is spider silk. I never directly work on a spider silk. My PhD advisor did. So spider silk, if we know the properties of a spider silk, we can characterize them in the lab. And it turns out if you make this back of the envelope calculation, if you upscale a spider silk, a pencil thick spider silk thread would be capable of stopping a Boeing 747 in full flight. That's how strong a spider silk is. And the remarkable thing about this is that spider silk is made of crappy materials that the spider can find in nature, right? Amino acids and proteins that are usually soft. So this feat is achieved through this hierarchical organization, right? So you have atoms, the atoms form molecules. How these molecules are arranged, it has a huge impact on the ultimate properties of the materials. So understanding what's going on at this scale of the atoms and molecules is incredibly important to develop better materials. All right, so just now to compare spider silk to the best polymer that we have, which is Kevlar. Kevlar would be the strongest polymer that we have. We make bulletproof vests out of Kevlar. Spider silk is orders of magnitude tougher than Kevlar. Toughness here is defined as the ability of a spider silk to dissipate energy. So the point being is that by organizing the molecular structure at the nanoscale, how the atoms are arranged with each other, you can create materials with amazing properties. And understanding how these properties come about, it became my job for 5 years, and I still do it. So the other component of what my postdoc was and my current research is not just the nanomaterials, that's the focus, is using computer simulations. So it turns out it's remarkably hard to do experiments at this scale, okay? And the best way that we have right now to study how materials behave at the molecular nanoscale is to put together mathematical models that we can simulate in the computer. And the simulations that we use to do this, which are my bread and butter, in these simulations, we describe the system at atomistic resolution. What that means is that we represent each atom in the material. And each of those atoms is a point particle. That means it's a point in a space with coordinates. And then the atoms interact with each other, right? When I mean with interact is that they make a force each other. And you can integrate the motions. The atoms move around depending on what those forces are. And they move around following Newton's equations of motion. So the most important input in this simulation is what we call the force field. Okay, the force field is just a function of the positions of the atoms. And what it tells the atoms is how they behave, how they interact with each other, right? So this is the way that you can have to simulate a water molecule or a Kepler molecule. So the algorithm that we use to simulate these systems, the force field just tells how the atoms interact with each other. The algorithm that we use to simulate it is called molecular dynamics. And what we do is first calculate the forces on each atom of the system. You can do this just based on this function that is called the force field. Okay, so we know how the atoms interact with each other. We can calculate the forces in the atoms. With the forces in the atoms, we can use Newton's second law and calculate the accelerations. Once you have the accelerations, you can update the positions and their velocities. All right, so repeating this over and over, what you end up having is a trajectory. So one of my simulations is like having a huge microscope that you can just zoom in into some material, have atomistic resolution, and see a movie of how it behaves over time. And this technique is very powerful. And in fact, it has been used to model pretty much any material that you can conceive. Ceramics, clays, glasses, metals, polymers, biomolecules. It's a very, very transferable technique. And of course, like everything else has limitations. And the limitations of this technique is that it's very computationally expensive. All right, so we are limited to systems that are basically of nanoscale dimensions, which, by the way, makes it ideal to study nanostructure systems. But again, there's always some limitations. Every technique has limitations. So a little bit about simulations. If you're not familiar, people hearing this talk, they are all different backgrounds. So how simulations fit on the framework of science right now. They have become, computing and simulations, the third pillar of science. So traditionally, we have experiments and theory. And now we have computer simulations. How do they fit together? Well, it's very simple. We basically use computer simulations to really deal with problems that are too complex to handle analytically or experimentally. Experimentally, we are usually constrained by, it's difficult, right? To look at this scale, this dynamic resolution, control the environment, the variables, is very hard. And then analytically, I mean, there is not that many systems that we can solve. We are very limited. And when I say complex systems, they don't need to be that complex. So for example, what you are seeing here in the movie is the three-body problem. These are three particles interacting with each other through gravitational forces. Well, we don't know the analytical solution to this problem. So three particles are already too complicated. All right, so this is where computation comes into place. Is extremely insightful, right? We can basically use these low-level theories to build a complex system, and then we simulate it and we see how it behaves. So that has basically revolutionized the way we study systems and materials in particular. And just a fun fact, the first simulation ever was performed, I don't know if, what you consider simulation in a computer. It was in the computer Maniac in Los Alamos during Second World War. The Maniac was designed by John von Neumann, and the director of the computing institute there at the time was Nicholas Metropolis. So the first simulation that they put together, it was a Monte Carlo simulation of a many-body system. So it looks a lot like the simulations that I run every day. A bunch of particles in a box, you tell the system how they interact with each other, and you look at how they move over time. So there's a lot of history behind simulations, very exciting history. So after my doctorate, I moved to Berkeley to do a postdoc now in computational chemistry. So how does a structural engineer end up in a chemistry department? That's because when you go to these small scales, trying to understand how basically in nature materials work at the most fundamental scales, physics, chemistry, engineering all gets fudged together. It's the same thing. So it turns out that in chemistry, this is where the techniques that I use to simulate my systems, they come from. So they are the biggest experts on this stuff. So I went there to learn. And you know, the set of techniques that I learned how to use there, they go even a little deeper than molecular dynamics. And we start looking at the electronic structure of atoms. So we are solving Schrodinger's equations, quantum mechanics. So that gives you range to study a whole set of problems that you didn't have access with MD simulations. Now, again, you gain accuracy, you gain some deeper level of understanding, you have to sacrifice something that's the size of the systems. These techniques are much more expensive to resolve. So, all right, that's my background. What am I doing here at the University of Miami? Became an assistant professor in 2019, and I call my research lab the Computational Nanomaterials Lab. There you see pictures of my graduate students. Some of them I co-advise with other faculty in the College of Engineering. And our goal is to develop physics-based guidelines for the rational design of nanostructured materials. So let me unpack this a little bit. So rational design, what does that mean? Well, that's opposed to trial and error. Trial and error has been the traditional paradigm of materials discovery. We do not understand how materials behave at the fundamental scales, which means that we cannot make them better. The only way that we have to make them better is try different things and see which one works. So rational design is trying to break with that, because obviously that other process of trial and error is expensive and very inefficient. So the overall focus is on nanostructured materials. Why? Because as I show you, the nanoscale, things get very interesting. And physics-based guidelines could mean it's a proxy for fundamental understanding. So the tools that we use to do this are multi-scale modeling techniques, which you already saw. That's what I did in my PhD and my postdoc. Theoretical models, they are crucial to interpret what the simulations do. And a year from now, I started looking into data-driven approaches. Okay, so I'm not a data scientist by training. I'm actually maybe becoming one. I'm learning. So we started using data-driven approaches because you'll see they are extremely well poised to solve some problems that have remained extremely challenged to approach with traditional techniques. And I want to show you, because it's important, and computation and simulation means different things to different people. So there is two guiding principles that really, these two quotes represent very well how I understand computation and what my interests are. So the first one is from Richard Hamming, and it says the purpose of computing is insight, not numbers. All right, so I'm not in the business of quantitative predictions. I'm in the business of understanding and really getting to the bottom of the mechanisms. When you change something, how does that change the behavior of the material? When the material behaves a certain way, why is in the structure that does that? And also, I'm not interested in just predicting things from the model, like my simulation spits one number, I'm good with that. I'm, again, trying in the business of understanding. Boltzmann put it very well, that nothing is more practical than a good theory. And we'll go back to this principle because it's important. So once you have a theoretical description, which to have a theoretical description, you need fundamental understanding, it's very easy to predict and generalize. So that's what we are after. All right, so that's me, that's what I do, that's my background. So I'm gonna jump into the second part of the talk, which is just a few thoughts on science and engineering and how data-driven approaches fit in this whole business. So the first thing that I'm gonna do is to, I guess, explain why some scientists struggle with data-driven approaches and machine learning. So the first thing is just basically an antagonistic reaction to these outrageous predictions that sometimes you see out there. So in 2008, and the Wire magazine, there was this article by Chris Anderson that said the end of theory, the data deluxe makes the scientific method obsolete. Well, it's 2021, I'm still here. So it's this kind of statements, this kind of hype that really make a lot of people uneasy with the progress of AI. But these predictions could be fine if they could realize, but of course they don't. So that's part of the problem too, right? That many of these predictions don't live up to the hype. And here I'm not gonna say a lot about it, because I could say slide after slide about how AI failed in certain, but that's not the point of this. And I would really, really recommend that you watch the Data Citizens lecture by Elliot Siegel that was called AI and the Presumed Death of Radiologists. So he explains this beautifully, and so I really, really recommend that you watch that. But I'm gonna focus on Andrew Ng quote that all of AI, not just healthcare, has a proof of concept to production gap. What that means to me, and it means to him as well, because he made this statement after working on a project where they have a Stanford hospital. They were trying to predict, diagnose basically using radiographies. And it turns out they developed a model that seemed to be working very well. They brought the model to the hospital down the street, and now the predictions were terrible. So that seems to happen a lot with AI and data-driven approaches. So generalizing is very hard. They are very bad at generalizing. And I have another anecdote about a friend. He's an actual electrical engineer. He's an actual data scientist. He works on image processing. So he had a multi-million-dollar DARPA project. And it was about biometrics, trying to identify people in movies, and so in videos. So their collaborators in Switzerland, they updated the software of the camera. That turned out to introduce a small bias that with the naked eye, you would never see it. And it didn't make the predictions worse. It just made them nonsense. And, I think this is what really scares people doing science. So the black box prediction is one thing, but not knowing why it works in the first place makes you very uneasy, because you don't know when they are gonna fail, when that prediction is gonna fail. So that's very hard to deal with. And oops, it's in there. Can you guys see the screen? Because my screen went completely haywire.
Yes. Well, it's pixelating a bit.
Yeah, weird. All right, let's try again. All right, that's good. So sometimes when I read some articles on AI, I ask myself, it sounds too good to be true. And it reminds me of these automatons in the late 1700s, where you have the robot that plays chess, but in fact there was a human inside the machine playing. So I guess in this analogy, the human would be, I don't know, overfitting or lack of generalization, right? You have all these AI models that are supposed to work wonderfully, but they really are not doing a very good job at generalizing. So anyway, generalizing is hard. To me, that's the biggest drawback of data-driven approaches. And science, on the other hand, is actually the opposite, right? Science, is, in my mind, the ultimate product of science is theory, is the art of generalization. And I'll try to explain to you what I mean with an example based on the way we design structures, okay? So in the Middle Ages, the way we design structures and infrastructure, it was by copy-paste. Somebody got to a solution by trial and error, and what we did is copy and paste again and again and again. You couldn't change much because you didn't understand why they were working in the first place. So what if you change the aspect ratio of the arc and then the whole thing collapsed? So this limits you a lot, right? You are learning, this is basically a data-driven approach. You're learning from data. So basically you can only speed up what you have seen already. But today we design anything we want, right? We can pretty much make a stand any arbitrary shape. And I would call this rational design. And what goes from copy-paste to rational design is fundamental understanding. Now we have theories. The theory doesn't depend on the minutiae and the details or where this bridge is or even what is it made of. We have theory that it can predict the behavior of the structure under a wide range of conditions, and that enables rational design. So in my mind, data-driven approaches are a lot like the copy-paste, and to get to the rational design and through predictions, we need some sort of theory. And of course, theories are not just all good. And in fact, they are not just by themselves good enough. I'm not gonna explain the spherical cow joke, but you can ask me at the end. So theories rely on idealized versions of the real world. That's true. So they get rid of a lot of complexities that sometimes are important. But the one good thing about theories is that the simplifying assumptions are known. So we always know what we left out. Okay, so that helps to diagnose when the theories don't fit. Theories sacrifice accuracy for interpretability. That's almost the opposite that data-driven approaches do. And ultimately, analytical models are, and this is the limitation of theory, is that they are limited to very, very simple systems. All right. So this is where computation comes into place and how it has fit so nicely in the scheme of science. So let me give you an example. You have a low-level theory. This could be quantum mechanics, right? So you understand how a water molecule behaves 100%. You know everything about the water molecule. And then you have a real-world prediction. For example, in the case of water, you know that ice floats in water. So that's the temperature of maximum density. So you know that water has a higher density, sorry, at some temperature, right? So how do you go from quantum mechanics to real world predictions? So you can make a computer simulation. You put a bunch of water molecules in a box. The interactions between the water molecules are dictated by the low level theory. Then you, and this is the important step, you develop a high level theory based on what you have seen in the simulation. And now when you see what the water does at different temperatures, you can see why the water has a temperature of maximum density. Because when it crystallizes, it actually has a lower density structure. So that's why ice floats in water. So this pipeline is very powerful. And by the way, I'm a computational scientist, so sometimes I forget about the experiments, but they really permeate the whole enterprise. Okay, experiments are needed to validate and inform at any step during this trip, from low-level theory to computer simulations to the high-level theory to the real-world predictions. So I actually think this pipeline works pretty well. So what I'm going to argue is that this scienceless approach, all right, where you have data collected by experiments, simulations, whatever you want, and going straight to the real-world predictions through a machine learning algorithm, a machine learning model, I don't think this is productive. I don't think it's going to work. And again, I don't think it's a good approach. So I believe the pipeline that we use to do science is good. In fact, it works. So if it ain't broke, don't try to fix it. So what can we do with machine learning and data-driven approaches? We can actually deal with a lot of challenges that arise at these different stages during the steps of doing science. So in particular, so how can machine learning contribute to some of these stages? So for example, machine learning can actually, and is being used to speed up computer simulations. Physics-based simulations are incredibly expensive. So machine learning approaches can be used and are being used, again, to accelerate those simulations. I read some papers where machine learning is started to be used to develop some low-level theories. That's a complicated, very interesting area of research, and I don't know if it will work, but it can be used for that. And this part that I'm more interested on is in this link between the output of computer simulations and the high-level theory. There is many systems that we study, and I'll show you in a couple of slides, that are complex, are heterogeneous, disordered, are messy. We don't understand how their behavior arises from their structure, okay? And that's sort of at the frontier of science right now. All the simple systems, all the systems that exhibit periodicity that we can describe with the structure property relations, those we sort of understand, but there's a lot of systems that we don't. And here is where I think machine learning has a great opportunity to create an impact. So I'm gonna now go into the third part of my talk, where I'll focus on a specific fundamental problem. I'll tell you what that problem is, why we are interested in it, And I'll tell you how data-driven approaches can actually help us move forward. So I didn't tell you my slide about my lab, but we are particularly interested in messy systems. So messy systems, I call anything that is disordered or heterogeneous. Okay. So here I give you 2 examples of projects I'm currently working on. They are both messy in their own way. So on the left, you have glasses, which is the problem that I'm going to focus more later on. And these are systems that have a structural disorder. Okay. The applications of this project would be for ultra durable cement, which would make sustainable infrastructure. I will explain that link too as well. The point here is that glasses are messy systems because the structure is disordered. High entropy alloys is another project that I'm gonna go into detail, but here the disorder is not the structural. What that means is that I know the positions of all the atoms in this lattice. Okay. I know exactly where the atoms are going to be. What I don't know is what type of atoms they are going to be. And that's going to change the properties of this system. So let's jump on with the glasses. So the first question is, what are glasses, right? So I'm going to try to give you a few examples, and then you have to think what they have in common. I think that's the most intuitive way of starting to think about glasses. So the first one is not going to be a shocker. So glass, the pane of the windows is a glass. Some polymers are glasses, okay? So they also look transparent. So, you know, there's something in common there. But now cement is a glass as well, all right? Cement we use to make concrete, to make buildings and infrastructure. So cement is a glass. There is metals that are glasses as well. So metallic glasses. Granular materials, a pile of sand can be treated as a glass, and ultimately traffic jams, all right, whether the cars or ants or any other animal system, traffic jams are also glasses. So at this point, you are probably more confused than about what a glass is that you were early on. So all these systems pertain to a class of systems that can be described with the same mathematical framework. All right, their dynamics follow some universal rules that can be described again with the same model, the same theory. And that's why they fall all under the classification of classes. What I'm going to focus on is materials. Okay, forget about the traffic jams, the piles of sand. Let's focus on these 3 materials right now, because these are glasses at very different scales. So the glass that you see on the left, the glass that you have on your windows, is a glass at the atomistic scale. What you are seeing here is atoms in yellow of silica, of silicon, and in red atoms of oxygen. And you see how it forms this disordered network at the atomistic scale. Polymers, they form a disordered sort of agglomerate of molecules, right? So polymers are made of these long molecules that they fold and they form these globular structures. And when you put a bunch of them together, they form this glass, this disordered structure. And cement, you have to go a higher scale even. And what you see is this, what we call nanoparticles. You see these semi-spherical particles that they basically stick to each other in a very disordered way. And each of these nanoparticles could be about 50 nanometers big. So here you see 3 materials whose dynamics are basically dictated by the same mathematical framework, and the scales are completely different. So, okay, fine, glasses, we kind of know what glasses are now, is disordered structures. Their dynamics are very slow. That's the whole key about glasses. They are sort of stuck in these configurations, right? So concrete, these polymers, glass is solid materials. So they are disordered and they are solid. So you may ask yourself, why are glasses so interesting? Why is this guy telling me about glasses? All right, so let's do this quick experiment. So if I show you this structure, okay, I tell you the atoms of a material are arranged in this way. What would you say this material is? In what phase it is? In a liquid or a solid phase? Just need one volunteer. Nobody wants to adventure.
Solid phase.
Solid phase, yeah. I think that's an intuitive answer. How about this one? If I show you this one, would you say it's a solid or a liquid?
liquid?
Well, it can be both. This is the exact problem with glasses. So this is what makes them so amazing. So in a glass, the structures of the liquid and the solid are very similar, but the properties, something like viscosity, can be 14 orders of magnitude different. So our whole interpretation of materials behavior is based on how the structure relates to the properties. And while in a crystal, what you are seeing here is a specific volume versus temperature. When you have a solid state at low temperature, it has a crystalline structure. When you go to the liquid, the structure is disordered and is moving fast. So we can we can explain this. The structure change, the properties change. With the glass, you have also that change going from solid to liquid, but the structure stays essentially the same. So this is very puzzling, and we still don't have a very good explanation for it. And in fact, I mean, glasses have been stated as this very big challenge in science. In 2005, Science magazine published 125 questions that remain unanswered, and they are fundamental importance. One of them was the nature of the gaseous state. The Nobel Prize in Physics in 2021 went to three people. Half of it went to Giorgio Parisi, who actually did a lot of work on the theory of gases, discovery of the interplay of disorder and fluctuations in physical systems for atomic and planetary scales. That's a proxy for gases. Philip Anderson, another Nobel laureate, say that the deepest and most interesting unsolved problem in solid state theory is probably the theory of nature, of the nature of the glass and the glass transition. And if you are not into physics and materials, but you are into data science, you should know that DeepMind are interested in understanding the glass transition as well. And we'll talk a little bit about this paper later. So a lot of people cares about glasses. Why? Because again, this extraordinary lack of relationship between the structure and the properties, which is what we base our whole understanding of materials. All right, so let's pose a problem. This is the problem statement. What we want to know is, how does the structure of the glass determine its properties and dynamics? We are confused about this. We don't know what this relationship is. So here in this formula, you have A is a property, and this property must be a function of where the atoms are, and then maybe the density, so how many are they at the temperature, right? So how far science has got us here, we have tried structural markers. That means that they are functions that we calculate from the structure that are based on physical intuition. I mean, we are human beings. We try our best. We think about functions that sort of make sense, and then we see if they correlate to the properties of the glass. It turns out that they don't. Okay, so our best physical intuition fails to solve this problem. And what is even worse, we sort of feel that there must be something encoded in the structure, but we don't know what we are looking for, right? So this starts smelling a lot like a problem that machine learning can solve. So one of the first books that I started looking at when I wanted to learn machine learning, it was called Pattern Recognition and Machine Learning. So hey, machine learning is good at recognizing patterns. So can we use machine learning to identify structural features, structural signatures that can correlate with the system properties of their dynamics? Okay, so that would be the reason why we want to use machine learning. There is something about the structure that is too complicated for me to understand, but the machine maybe can infer. All right, so this is a general problem statement about the structure of the glass, the property of the glass. We are particularly interested in this phenomena called creep. All right, so if you have a cylinder made of concrete and you apply a load, and this load is not very high, but you wait long enough, the cylinder is gonna get shorter and shorter, it's gonna deform. And then when you release the load after a very long time, there's gonna be a permanent deformation. All right, so this is a low load, below the yielding point of the material. So this phenomena is a little bit hard to understand. There is something happening at the microscopic scale and the nanoscale that is making the material deform, and we don't understand that relationship. So creep is a problem for infrastructure because it limits its lifespan. And when you limit the lifespan of infrastructure, that means that you have to change infrastructure, renovate it, and repair it much more frequently. So it just stands to reason that increasing the lifespan of infrastructure will reduce the consumption of cement, which is the main material using concrete infrastructure. And cement is associated to a very high fraction of anthropogenic carbon emissions. So the idea here is, if we understand how creep depends on the structure of cement, we can make microstructure of cements that resist creep. And that could make infrastructure to live longer, which means that we need to repair it and change it less frequently. Now, of course, we don't understand this relationship just yet. So this is the problem that we have in mind, is the application. We want to make cement, the microstructure of cement, in such a way that it doesn't creep, okay? So what I'm gonna give you now in the next like 5 minutes or so is sort of an overview of what people have done, okay? And there's a lot of technical details here. I tried to go over, gloss over them. So again, if you have a question you want to go over after the talk, any of these details, we can. I'll try to give you a very high-level view of what people are doing and where we stand right now. So one important thing to mention is that all the machine learning models that are out there, everything that people are trying to do, are trained using data from molecular dynamic simulations. So a simulation could look something like what you see here in the cartoon. What we are applying is a shear force. So you have a box full of atoms, particles. This is the glass, and what we apply is a force, okay? We apply a force, and we look at how the glass, the system, deforms over time when we apply the force. So the output from the simulations is just the positions of the particles as a function of time. So this is basically an experiment where we apply a load, we see how the system deforms. From the position of all the particles, what we can calculate, one thing that we can calculate is the particle displacements. Not all the particles move the same, okay, as a function of time. Some particles move a lot, some particles don't move so much. So particle displacements, we'll see later, that is one of the things that people are trying to predict. It's like, if I apply a force to this system, can I predict how much the different particles are gonna move? And the output of one of these simulations, what you see in this plot, is in the x-axis is shear strain. That's a measure of deformation, how much the system is deformed. And in the x-axis, you see the number of load cycles. So the force is applied in cycles. It's a proxy for time, all right? So we know how the system deforms over in time. And now the idea is to use machine learning to try to tell us something about the structure, okay, that can either predict the displacement of the particles or how the system deforms over in time. All right? So now I'm gonna switch to what people are doing in terms of machine learning models. So the problems are stated in the following way. People are using currently, right now, they are using classification methods, logistic regression, support vector machines, gradient boosting decision trees. And what they are trying to do is classify the particles in a glass as mobile or immobile. And this is based on the value of their displacements with respect to some criterion. So I'm not gonna elaborate a lot on the criterions, but basically from the simulation, for example, the one on the left, what you are seeing here is the probability density of the displacements of the particles, right? So it looks like a chi distribution, actually. So there is some particles that deform very little, there's an average, and there is some particles actually that move a lot. So what they call this tail, this area in red here, is what they are considering these particles that are mobile, and all the other particles are considered immobile. So this is kind of an ad hoc criteria, but this is where the field stands right now. We are trying to just classify particles in a box as mobile or immobile. And each particle here is an example, okay? So not the whole system is a data point that we are gonna describe with features. Each particle, each atom has a displacement, which is the stuff that we want to predict, okay? And each atom, we have to describe it by features. So the features that are used in this problem are based on the local structure, so what atoms see around themselves. So what you see here on the top is an atom, is in red, all right? And it has atoms around it. So what you can measure is the distance between the neighboring atoms. You can measure areas between triplets of atoms, and you can even measure volumes when you build a tetrahedron between neighboring atoms. And then you can gather metrics, statistics of the neighbors metrics, etc. So the idea here is take an atom, okay, and you describe the local structure as best as you can. So these are all handcrafted features, okay? The ones on the bottom are a little harder to understand, but it's just a symmetry function that, again, is related to the structure of that atom, okay? So what environment that atom sees around itself. So all the models so far, or most models, we see the DeepMind approach is a little different, are based on these handcrafted features. And okay, so we use support vector machines, for example. We describe each atom by these features, and we assign to each atom some displacement. So what we can do is just train the model, all right? And we classify between mobile and immobile. So again, just hold on to the visual of SVM. So in SVM, you basically calculate a hyperplane that separates the two classes of atoms. So what people have done is develop this metric that is called softness. So this could be that machine learned structural marker. This is a function that we as humans cannot derive, but the machine has identified. And they define softness as the distance of each of these atoms to the hyperplane. Okay, so if an atom basically is close to the boundary, it's not very clear if it's mobile or immobile. If it's very far from the boundary, it is very soft, or very hard, right? So that's the intuition. And these are different studies. What you see here, the colors are basically classification of the particles based on this softness, which is a little bit odd if you think about it, because what they do is use a classification scheme and then use this distance to the boundary, separating boundary, to establish a continuous metric. So that seems, it's not a very intuitive two-step process. And I don't know if that's optimal. One thing to notice is that 99% of the people working on this problem using data-driven approaches to solve it are not data scientists. They don't come from that field. So I think cross-fertilization will be extremely beneficial for both. But anyway, here, what you see on the top right, let's just look at this plot for a second. You see on the x-axis is this metric of softness. So particles that are very high softness they can move a lot, all right? And particles that they don't move a lot. So you see that the distribution of softness in the system is a Gaussian with mean 0. That's the black curve. And then the red one is the probability that a particle is soft and that it moves a lot, it rearranges, right? So 90% of the particles that are about to rearrange have a softness higher than 0. So it's related. They find basically a machine learned structural marker that really correlates with whether these particles move a lot or a little. One study, which is very interesting, look at the inset in this plot here. On the y-axis, you have the average softness. All right, you take the softness, and this softness is actually not defined as in this case because the average would be 0. So the average softness of the system as a function of time goes down. That means that the particles become harder to rearrange. So that's correlated to the creep rate, right? So how these things deforms over in time. So there is some progress to some predictions based on these metrics of softness. That's basically it. The other thing that I want to mention is, because it's remarkably different, is the approach by the DeepMind group, which is based on graph neural networks. So in this case, forget about the handcrafted features. What you do is build a network based on the connectivity of your glass. So you define for each particle a cutoff distance. You basically construct nodes between the particles that are within that cutoff. So that way you can create a graph, okay? So you assign features to the nodes that are just dependent on the particle type. The particular glasses that are being simulated have 2 types of atoms. And the edges of the graph are here the relative positions of the features, all right? So this is a qualitatively different approach than just using SVM or classification. And the goal of the graph neural network here is to calculate this propensity, which is the mean displacement of particle I at time t, right? So it's again this idea of how much individual atoms are moving and how much that depends on their local structure. So what they found actually is it's a little poor. So in the y-axis here you have a Pearson correlation coefficient. This could be high is good. This is the Pearson correlation coefficient between predicted values and true values. right? And what you are seeing here in the x-axis is the box tilt. So as you keep deforming your system, how good are you predicting these displacements, right? So, well, what you can see is that the physics-based metrics, this purple and red, are terrible. I mean, they are completely uncorrelated. So that's why we are struggling in this field with the physics-based stuff. We are completely lost. But even the graph neural network is actually not great. You have a Pearson correlation coefficient at best as over 0.5. So there is still a lot of work ahead. I want to say something about the graph neural network, which is, I thought it was very interesting, that even if you don't assign any features to the nodes or edges, just the structure of the graph gives you almost the same performance, all right? So what you are seeing here on diamonds, empty diamonds, is when you use all the features. And again, y-axis Pearson coefficient, high is good, low is bad. In the x-axis here, you have time. So as a function of time, how good are you at predicting the displacement? So what you see in these gray and green dots, they are the graph neural network without features assigned to the nodes or the edges. And they perform, at short times, they perform much worse than the graph neural network with all the features. But at long times, you know, when the system is kind of uncorrelated, they perform almost as well. So I thought that was very interesting. I think there's a lot of promise of using graph neural networks in the class problem. Now I have to give a minute to the work that we are doing. Actually, I'm collaborating with Melvin Ayala and Amit Sarafraz. We have been collaborating for a while, but it has been complicated because we come from such different places and it's such a complicated problem. But we are making a lot of progress, and I think it's been fun on both sides. So what we are doing is trying to also predict displacements of particles. That's why everybody's doing this. Is the first time we deal with this problem. So we were trying to get to a point where we understand what we're doing. And to do that, we are using deep neural networks. And we are actually interested, we are not interested in classification. I don't understand that that's the goal of the other methods either. They first classify, then they do softness. It's weird. So anyway, we are trying to predict displacements, and these are some preliminary results that Melvin got. They are encouraging. We are still working towards it, but we are working on it. So I'm almost done with the presentation. I have a couple of slides. One is next steps, things that I think are very promising and that we should do, and they are big questions. If you solve them, you get your name out there. So the first one is collective mechanisms. I won't talk a lot about this. This is more for physicists. The second one, very important for people experts in machine learning. We need to make these machine learning structural markers more interpretable. Right now, we got them, but we don't really know what they mean. So it's very hard to use them. Another thing that we want to do is, this is like a dream pipeline, right, of things that we want to do. Machine learned surrogate model that can simulate creep. You just feed it a structure and it gives you the form structure after some time t. And the point of doing this is that the physical simulations that we use to train the models are very computationally expensive. So a surrogate model to simulate creep would be quite a tool. Ultimately, we are interested in designing better cement, right? Better microstructure. So there may be some opportunities on generative machine learning models to basically output creep-resistant colloidal microstructures. So the problem statement would be there, all right, if I have to pack n of these atoms in a box, how would I do it such that I maximize the softness, for example? So I think this is a very also interesting problem. All right, so the take-home messages that I have, I hope I convince you that machine learning is really not there to replace theoretical models, but however, it can contribute uniquely to many steps along the pipeline of science. So that's what I think the strength is. Machine learning models trained with physics-based simulations are uniquely poised to provide insight into complex systems like glasses, right? Once we are dealing with messy systems, we need machine learning to identify these structural patterns. And honestly, the traditional approaches, we have hit a wall, so we need them. These structural markers that we have, so the research that has been done so far, is a step in the right direction, but the interpretability is still very low. So it's not very clear what we learn. And the last thing, I hope I convey that glasses are incredibly interesting systems. Cement is a glass, so you may have never thought about it that way, but cement is therefore an incredibly interesting system. So with that, I would like to thank you, and I'll take questions, if any.
Well, thank you very much. Thank you very much. Yes, that's what we miss at the end of a nice talk, Luis, is we don't get to have applause. While people are thinking of questions, we have just a few more minutes. There's some in chat. No, it's basically saying type them in chat. While they're thinking of that, I should ask you, in Santander, which is just a bit east of Bilbao and San Sebastian, are you? And you began with elephants. Do you have an interest in anchovies by any chance?
Oh yeah, they have very good ones, very expensive ones. There is a place close to Santander called Santoña, and they are famous for their anchovies.
These are Cantabrian anchovies. There's a rivalry in Spain between the north and the south, you understand?
Yeah.
And in fact, modeling of anchovy systems in migration actually isn't something that lends itself to computational modeling. That will be our next talk. Please, some questions from participants today.
I can start a little bit, if and I know that we don't have that much time. So I think that this was a great talk, Luis, and I really appreciate. And it's a question and a comment. If you can, take it into the next level, and I think that you touch it very well, right? So machine learning is a technique, right? It's not really a science on itself. So the idea there is and what we call it here in the Institute is that the data science is the scientific process of how you actually approach a problem. And using the data to actually do the scientific process and discovery, as you mentioned. So there is a lot of hype and there is a lot of marketing words about machine learning and AI. And it's not even just machine learning, it's actually supervised machine learning when people are talking about, right? It's not even, other forms of machine learning or other parts of this. So I think that you bring the point very well. And the question there is that, traditionally we had the different levels of science, and then computational science came along with the simulations. But now it's the data science, because now the simulations generate a lot of data, which they can then drive us to make better decisions and perhaps better simulations, as you said. Can you elaborate a little bit about that and how you see this? Because I think that what you touch it is actually a very important and interesting point that moves us beyond the today's hype, if you will.
Yeah, that's exactly right. I can tell you how that works in the field I am. So I'm ultimately interested in discovering better materials, right? So these are materials that don't exist. So in that arena, simulations give you an edge over experiments, because you cannot do experiments on something that you don't know, right? But you have to spend time and money trying to see how you even fabricate it. So simulations are this beautiful tool to basically gain insight into things that are not yet. And then machine learning is craving for data. So I think it's a relationship that has been really underexploited at this point. And maybe part of it is because a lot of the machine learning is related to maybe industry. So, email, so completely different applications that is science. Like you don't use computer simulations to generate a spam email or movie recommendations. So a lot of the progress that has been in machine learning is in problems that really physics-based simulations don't even play a role. But when we are talking about science, I think the combination is incredibly powerful. I have to say too that even now, computer simulations, you would think that they have been established as, I saw the third pillar of science and everybody accepted them. And that's not completely true. People are skeptical of the models too. In many programs in NSF, you cannot apply I cannot apply alone. If I don't bring experiments along, they won't fund me. So, it's a struggle we have to go all through. And I think it's very important. And we did this mistake on the simulation field, and people still do it. I think overselling yourself is a mistake. Because when you don't, accomplish what you say, it's like, what happened? And if every paper that is published is like, we solved the problem, it's like, why do we have the problem 20 years later? So I see a lot of relationships between computational science. We need to start the simulations, and now data science being incorporated in science. And I mean, the opportunities are massive.
And that strikes me as a very wise way to begin to wrap things up, by the way. We can oversell iDisk, though. So congratulations on a wonderful talk in this episode of iDisk. The last question came from Nick Centeramus, of course, the director of the Institute for Data Science and Computing. Another shout out to Eve and to Giannina for all their help and work. You see on the slide that's there, the next presentation is on December 8th at noon, when Xinghua Chuang will be giving a presentation as part of the Meet a Data Scientist series. Luis, thank you so very much for this really exciting talk. And on that note, unless someone else objects, we do want to try and stick to the time. Nick,
there was one question that just popped up, but I know we're a little bit out of time, so I don't know if you want to talk about it fast.
I do. I don't know if you guys have to kick us out, but...
We don't have to kick you out. You have the floor.
All right.
We'll just charge Giannina the rent. Please, the question there, Luis. Please read it if you would and answer it.
I'll read it myself from the chat. So about the machine learning scheme for creep, can it be tuned toward the physical/chemical interactions that are happening, or is it just a function of the current particle positions? Absolutely, yes. So how the material deforms over time depends on the structure of the material, right? On the positions of the atoms and how the atoms interact with each other. So when I basically when people are neglecting the chemical interactions would make a material specific, right? Are you simulating cement or are you simulating this metallic glass? What people are after right now is some sort of universal description of classes. So that's why you see all the systems that you have seen there, all the studies that are done using machine learning to basically learn this glass structure correlated to the dynamics are based on model systems. This is where we are. It's very basic. The people caring about this problem too, they are not concerned about exact, precise materials where the chemistry will play a big role, right? Because it's not the same if you have you are trying to predict creep in concrete, or a pane of your window, or a PMMA glass that is bulletproof. That would be, in my mind though, that would be more the engineering, right? Once you have figured out the fundamentals, you basically go and specify for different systems. So I hope that makes sense.
Super. And the success in this work, as you know, one of the things I learned was that the manufacture and use of concrete produces more carbon than international air travel. And getting this right, getting these simulations right, I think is an important step in the way to trying to address that sort of challenge. On that note, do we have another question? We could be on a regress here. Thank you. No, we're all set. Nick, anything else to ask?
No. Thank you.
Beautiful. On that note, Luis, thank you again for a very nice talk. Thank you all for being here and for participating in the Meet a Data Scientist series. Until December 8th, hasta la vista.
Thank you.
Thank you all.
Thank you.